Hello, my dear NEET warriors. Welcome aboard to your favorite NEET English channel. And this is your Captain Shreyas, your physics educator. And in today's class, we are going to learn everything about the galvanometer, the voltmeter, the ammeter, and also the potentiometer. Basically, all the important electrical instruments. All right. In current electricity, the detailed marathon, that one shot which I conducted, I have, already discussed one particular instrument which is called as the meter bridge, which is based on the principle of Wheatstone's bridge. So that instrument is already covered there. In case you want to check the theory, please watch that particular detailed marathon of current electricity. You can think this is basically the extension of your current electricity chapter where we are learning all these important electrical instruments. So before we proceed ahead, make sure you show your love, you smash the like button and call in all your friends, all your batchmates to this particular session because it's a fun-filled session, lots of learning outcomes today. Hello Nandu, hello Sangeeta, Murugwai, Veli, welcome Subhashri, Jimmy, now hello Hari, hello Mark, hello Buddha, hello Priyanka, hello everyone, nice to see. So we'll be doing next lecture tomorrow, and make sure that you are tuned in on the channel. I will show you and I will share with you the exact plan on the Telegram channel as well. So make sure you are following me on the Telegram channel and also you are subscribed so that you know what is the next lecture. Obviously things will continue in progress. Whatever chapters are remaining will continue. Don't worry about it. All right. Hello Kirtana. Hello Rakshita. Welcome. Vadanjini. Nice to see all of you back over here. So let's start talking about basically galvanometer. Now, how does a galvanometer look? First, let's see that. So, galvanometer usually looks something like this. Okay, maybe, yep, something like this. And you will probably see one dial over here. There will be one needle. There will be some markings on it, something like that. This is how a galvanometer looks, and probably you will see one terminal here, one terminal here. This is one wire and this is one wire. That's how usually a galvanometer looks. The scale of the galvanometer has 0 and it has some divisions over here, and it also has some divisions on the other side of the 0. This is the positive side. This is the negative side of the galvanometer. There is a maximum reading that you can get. On both the sides. This is your 0 marking. So this is your maximum division I would say on either side. This is how the scale looks like, and your needle could be anywhere, left side or right side, doesn't matter. Basically, let's say it is over here. So then this is your deflection. This basically theta is nothing but your deflection. So that's how it looks like, and that's how the needle moves. There is some deflection, it will show some reading and all of that. Now, what does a galvanometer actually measure? A galvanometer basically measures current flowing through it. So a galvanometer, the symbol for that, some people just put G over here, or some people just try to put this arrow mark and then put G over here, one and the same thing, don't worry about it. It basically measures the current. What does it measure? The current flowing through it. Measures the current which passes through this orange wire which I have shown. Is that clear, my dear warriors? Everybody? How many of you have seen a galvanometer in your lab, in your school, in your college? Let me know. Okay, you can see that there is demarcations over here. There is always one division, small division. This is your max division. Sometimes it is also called as, your full scale. Sometimes it is also called as your full scale reading or the full scale measurement. All right, so that is your maximum value that you can measure. There is 0, there is negative, there is positive side. Now, why are there two sides? Can you guess why there are two sides, positive and negative? Think about it. There is one simple reason for that. If I have a galvanometer and let's say there is current flowing through it, and that is I, and I tell you theta is basically the deflection, theta is the deflection, then this theta particularly is directly proportional to the current passing through it. Theta is basically directly proportional to the current passing through it. Not just that, if there is no current, then it just means there is no deflection. There is no deflection in it. Not just that, if by chance the current goes in one particular direction, then the deflection is positive. If the current goes in the other direction, then the deflection is negative. That positive and negative is basically just to show you the direction of it, whether it is going this way or that way. But otherwise, the magnitude of the deflection, whether it is 30 degrees or minus 30 degrees, is proportional. The deflection's magnitude is directly proportional to the magnitude of the current passing through the galvanometer. This constant of proportionality depends on many things, like how much is the coil's area, how many turns are there, and there is a spring inside a galvanometer, there is a magnet inside a galvanometer. It depends on the field of the magnets placed inside. So all these things decide the proportionality constant. So we will learn about that construction of the galvanometer in another chapter of magnetism, because we have not yet learned magnetism, so that's why don't worry about it. Just remember, oh, the deflection is directly somehow proportional to the current, and it is completely based on the principle of magnetic field. Magnetic field applies force on current carrying wires, so it is based on that particular principle. Just keep that in mind. Is that right? Everyone with me on this? Awesome, awesome. Now, whenever you have a galvanometer, that galvanometer has a coil, that coil has some resistance. So Rg is basically the coil resistance, of the particular galvanometer. Keep this in mind. Always this coil resistance is usually you will see is going to be very small, because the coil is made of copper or some very good conductor. So that's why the resistance of that coil is very, very low. Keep this fact also in mind. Also, there is a limit till which current can flow inside the galvanometer, because the moment from 0 you reach basically the full scale reading. Think about it. This is when there is no current, this is when there is maximum current flowing through it. This is basically your theta max. This is your maximum deflection which can occur. This will happen when maximum current is flowing through it. This coil might get heated up, it might just explode, it might just burn, it might heat up, and it might damage the instrument. So that is the maximum deflection that can occur at full scale. So that current is also called as the full scale deflection current that produces your theta max. You cannot have more current than that. Keep this in mind. Is that understood, my dear students? Is that clear? Everybody with me on this? So that is the maximum current always associated with a galvanometer. That is also usually very small, because the coil resistance is small, so it can easily get heated up and all of that. So large current can flow through the galvanometer, and then it can damage it, definitely, because the coil is very thin, it is very small coil, so very easily it can get damaged. Keep this in mind. Now that you know there is also maximum current which can flow, you also know that there is a coil resistance. There is another parameter associated with a galvanometer, and that is called as the current sensitivity. What is it called? Current sensitivity. This current sensitivity is nothing but how many divisions will that coil deflect, divisions which the coil, that needle will deflect per unit current. Say for example, there are markings over here, let's say there are 20 markings over here, and the maximum current that can be measured is 100. If there is 20 divisions here and the maximum current is 100, so basically 20 divisions upon 100, 20 divisions upon the 100 amperes, let's say. So basically it will be nothing but 0.2 divisions per ampere. So that is how divisions work, per milliampere or per ampere. So that is your current sensitivity. So current sensitivity tells how many deflections or how much divisions, how much angle do you move per unit current. So that is the meaning of current sensitivity. Is that clear, my dear students? Everybody with me? Can we do some problems now? Can we do some problems? Hello Hazel. Hello everyone. Yeah, no, it is not like a battery, Gorilla. No, it is not like a battery. Battery, is completely different. It provides electrical energy and it does work. It converts chemical to electrical. Galvanometer just measures current, nothing else. Okay. Now, why do we study galvanometer? Because you can take a galvanometer and do some modification onto it, and you will see that it can be turned into a voltmeter, and you can do one more modification on it and you will see you can turn it into an ammeter. So when you buy a voltmeter or an ammeter, actually you are buying a galvanometer which has been slightly modified. So in ammeter you will see there is one extra resistor which is there in parallel, and in voltmeter you will see there is an extra resistor in series with the galvanometer, which makes it a voltmeter. And they just change the scale. Instead of milliamperes they will put amperes or whatever, and that's it, they will sell it to you. That's all. So when you buy an ammeter or a voltmeter, remember it is actually a galvanometer deep inside of it. So you pull out the mask of the thief, you will see that actually it is nothing but a galvanometer. That's why we study galvanometer first. So maybe we should start with some questions coming up on your screen, and here is the first one. There are 50 divisions on either side of the galvanometer. The full scale deflection current is 2 milliamperes. That's the maximum current which can go. Then the sensitivity is, come on my dear students, what do you think? Okay. Sumo, how can I conduct test series, bacha? It is impossible to conduct test series on YouTube, no? You have to mark the questions. You have to give it on time. If I do it on YouTube, how will you conduct test series? It's not possible. So that's why we have the test series for just 999 rupees. It's very affordable. Join the test series. It's very simple. Okay. So you get first parts test syllabus, or basically chapter wise tests which are there, and after the chapters are completed you have the full syllabus test series. So there are 24 test series just for 999 with discussion for all the tests, with solutions which are given during the discussion, and you also get the questions, you get to know the analysis, everything. So 999, what more you want? Okay. Oh, answer is already marked. Why is the answer marked? Don't tell me the question was on the next slide. Oh, I think I just moved the slide by mistake and I went to the next one. Anyways, so the answer is C, but let's see how do we get it. The question is basically sensitivity. So sensitivity is nothing but the number of divisions that you go per unit current. Now it is clearly mentioned that there are 50 divisions. So 0, 1, 2, 3, 4 till 50. So there are 50 divisions. On either side, you go this side or that side, it's the same thing. And the maximum current that you can get is 2 milliamperes. So 2 into basically 10 to the power minus 3. So basically this is nothing but this is 50 by 2, which is 25. This is 25, right? And this goes on the top into 10 to the power 3 basically. So that many divisions per ampere. That many divisions per ampere. That's what it will be. So per ampere there will be 25 into 10 to the power 3 divisions. But for 1 milliampere, 1 milliampere is 1,000th of that. So can I say this will be nothing but 25 divisions per milliampere? 25 divisions per milliampere. Everybody with me? Understood? Yes. I hope that is clear. I hope that is very clear. So 25 would be the answer for this, right? So as simple as that. Moving on to the next question up on your screen. A galvanometer coil has a resistance of 10 ohms, sensitivity 4 divisions per milliampere, then 100 divisions on the scale. Then the maximum potential difference can be applied is, come on, think about it. Suma, you have the NEET Avenger batch, the NEET Energize batch, where the syllabus has already progressed till a lot. And trust me, till whatever tests have been conducted till now, whatever we have taught, at least whatever I have taught on YouTube, the same things have come. The same syllabus has come. All right. So the last recent test was on Newton's laws. Newton's laws is already done here. So there is no reason to worry. Even if some chapter comes ahead or behind, you can skip the test, you can give it again later on. So don't stop yourself. These are all excuses that, oh, the syllabus will not match, this will not happen. These are all excuses for not, giving the test. Don't give these excuses. A galvanometer coil has resistance of 10 ohms, sensitivity so much. If there are 100 divisions on the scale, then the maximum potential difference which can be applied. At the end of the day, galvanometer is a resistor. When there is current through the resistance, there is voltage which is created. So you can think as if the galvanometer has some resistance, there will be some current and there will be some voltage which will be produced. If maximum current flows in it, there will be maximum voltage produced in it. So that maximum voltage will be nothing but I max into R accordance to Ohm's law. In accordance to Ohm's law. The problem is I do not know I max, I just know the resistance. So for that, use that given piece of information. Read this carefully. There are 4 divisions per milliampere and there are 100 divisions on the scale. So if there are 4 divisions per milliampere, okay, and I tell you there are totally 100 divisions, these are the maximum divisions that are possible. So how many milliamperes will you get for that maximum 100th division? So every 4 divisions 1 milliampere. 4, 4, 4. How many times will you put? 25 times to get 100. So how many milliamperes can you measure? So basically 25 milliamperes is the full scale deflection current. Full scale deflection current. Agree or disagree? 25 milliamperes will be the maximum current that you can measure. Now put the 25 over here and you shall get the answer. This is 25 milliamperes. So 25 into 10 to the power minus 3 into basically 10. So this will be 25 into 10 to the power minus 2, right? So this will be nothing but 0.25 volts. So 0.25 volts is option A, I believe. That's the correct answer. Perfect. That is the correct answer. Is that clear? Yep. Varun, the classes are regular. Don't say the things which are obvious and which we are doing. Please keep the classes regularly. What am I doing now? Am I not taking classes regularly? So stop unnecessary spamming over here. Don't distract people, or else you can watch the lecture later on. Okay? If you want to distract, you can go somewhere else. Alright. So moving on to the next one. Moving on now to the next one. Coming up on your screen. That is your voltmeter. That is your voltmeter. Voltmeter, like I said, is used for measuring voltage. It is used to measure voltage, and at the end of the day, it is a galvanometer only. But it has been modified slightly so that it behaves like a voltmeter. It shows voltage instead of current. How do you do that? Let's understand. First, number one point. When you have a device, right? When you have a device, keep this in mind. If you want to measure the voltage across it, you never connect a voltmeter with the device, along with the device, one after it. You always connect it in parallel. So a voltmeter, number one, is always connected in parallel to the device across which you want to measure the potential difference. You want to measure the potential difference. That's how you connect the voltmeter across these 2 points. How much is the voltage drop? 2 volts, 5 volts, 100 volts, whatever it is. Now, if I want to connect the voltmeter in parallel to the device, should the resistance be very high or should the resistance be very low? Or it doesn't matter? Let's understand that. Imagine some current comes inside. The current has 2 options, to go through this and to go through this. Some current will go here, some current will go here. Now, if the voltmeter has very low resistance, lot of current will go through this, or most of the current will bypass and nothing or very little current will go through the device. So if this was a heater or a washing machine whose voltage you are measuring, suddenly you see all the current flows through the voltmeter, hardly any current goes through the device, and you will see the device will not work only. That is meaningless. You want the device to keep working normally, how it is, and without doing much, you want to measure the voltage. It's like, imagine you want to do blood test, whether you are B positive or O negative, whatever, you want to do blood test. So when you do blood test, what do? You take a small blood sample, na? It's not like you take one bucket of water and then like, okay, let's measure the blood sample, let's see the blood sample and let's see what it is. You are killing the patient. So same way, when you want to measure the voltage across this guy, you will not kill that device. You would be like, okay, we'll take a small current through it. We'll take a small current which is being bypassed, and that small current will tell me how much voltage is dropping over there. By measuring the current, we can measure the voltage. If small current has to go through the voltmeter should have very high resistance. So this will be a high resistance path. So most of the current continues to go over here. Keep this in mind. Is that clear, everyone? So a voltmeter has very high resistance. Keep this in mind, number one. In order to make the resistance very high, in order to keep that resistance very high, what you do is you basically take a galvanometer and connect it in series with basically a high resistance resistor. Connect it with high resistance resistor. Together these two, you just call it as the voltmeter. That's it. This is just nothing but the voltmeter. You take a galvanometer, connect a very high resistance, that's it, it becomes a voltmeter. But make sure that you erase the markings on the galvanometer, because it will all be in milliamperes or microamperes or picoamperes. Remove that and you calibrate it and write the new markings on it. 2 volts, 5 volts, 6 volts, whatever. So you keep the galvanometer as it is, but remove the markings on it and then redraw the new markings, or remove the numbers on it and rewrite those new numbers. Instead of amperes, it will be now in volts. So basically when you convert it into this thing, so the scale is calibrated for voltage now, for voltage. So basically it measures voltage by indirectly measuring the current through it, indirectly measuring the current which passes through it. That's what it is. Everyone with me on this? Everybody with me on this? Perfecto. Now let's understand what exactly goes inside the voltmeter. Let's understand how the current flows, what is the voltage, everything inside the voltmeter properly. So let's draw the proper diagram, systematic diagram. So you show the galvanometer. This is basically Rg. You show basically this is Rg. This is the galvanometer's coil resistance. Remember, every coil has a resistance. You attach one more resistor in series. This is your series resistor. That's it. And together these two makes up your voltmeter. This makes up your voltmeter. That's all that is there in a voltmeter, a galvanometer and a series resistance. So this point is connected at one point, this point is connected at another point across the device. So the device will come over here. This is your device. Which is now like this. Perfect. This is how it is. You would want that whatever current comes in over here, most of the current continues to go over here. Very little current goes over here. Very little current will go over here. Is that right? And you will see again the current collects back like this, right? So this is how it goes. Very little current goes. Whatever this current is going, let's say I call that particular current as Ig, current going through the galvanometer side. This is basically Id, current going through the device. This is the actual current entering. So technically speaking, I is basically ID plus nothing but IG. But remember, IG is very, very less as compared to ID. IG is very, very less as compared to ID. So therefore I can say I is approximately equal to ID only. This current is approximately this current only, because very little current will go over here. Is this approximation very clear? And how did I write this? Using basically Kirchhoff's current law. Using Kirchhoff's current law, I have written this particular statement. Next important point. There will be some potential difference across the device. There will be some potential difference across the device. That potential difference, the potential difference across that particular device V, I can say it is IR, that means this current into this resistance, or because this is parallel to this, I can say it is this current into this resistance. This particular current into this resistance will give me the total voltage across this, right? I can write it as ID into the resistance of the device. I don't want to do that because I don't know either of them. Instead, I can say it is IG into the resistance of that voltmeter. What is the resistance of that entire voltmeter? It is series resistance, so RG plus RS. Don't you see the voltage reading is proportional to the current? So don't you see that the voltage is proportional to the current? But we also know angular deflection of that needle is proportional to the current. So can I say theta will be directly proportional to the voltage? So more voltage, more deflection. So you can see it has now been converted into a voltmeter. You can see now it has been converted into a voltmeter. More voltage, more deflection. Indirectly, by measuring current, you are measuring the voltage. By measuring the current, you are measuring the voltage. That's all. That's what happens inside a voltmeter. Is that clear, my dear warriors? This is a very important formula. Again, for solving voltmeter problems, this formula will help you a lot. Not just that, even this analysis is very important. So I will star mark this analysis. Keep this in mind. Yep. RS means stopping potential. How is RS going to be stopping potential? No, it is not shunt. What is RS? Oops, my goodness, thank God you guys asked. And I have told you this also while I drew this diagram. RS is nothing but, what is this RS? It is nothing but series resistance. Series resistance, not shunt. Series, S stands for series, not shunt, not stopping. No. It is series resistance. Remember, shunt means parallel. Is this in parallel? No. I know the symbol is same. You will see that when we go to ammeter, we'll be drawing a resistance in parallel. We'll be labeling it as RS, but there RS stands for shunt. Here S stands for series. Please keep that in your mind. In fact, I told it to you right over here. RG with series with this high resistance, series. So RS stands for series resistance. Keep this in mind. So all these are important pointers for voltmeter. Right? So voltmeter has a very high resistance. It draws in very little current. It lets the device function as it is without affecting the current so much. So most of the current still flows through the device. That little current is enough for me to show that the deflection is directly proportional to the voltage. And this is the main formula for the voltage difference. That's all. Alright. So let's start with some questions. Here comes the question up on your screen. There is some student. He connects a voltmeter over here and he connects an ammeter over here, and he uses a resistance, and he wants to do this experiment for basically Ohm's law, and he wants to measure how much is this resistance. So he measures the voltage to be 20 volts and he measures the current to be 4 amperes. So what do you think? Is the resistance going to be 5, more than 5, less than 5? Because we all know resistance is voltage divided by current. So one would say voltage is basically 20 volts, current is 4, so it is 5 ohms. But I don't think the answer is 5 ohms. I don't think the answer is 5 ohms. Can you guys tell me what should the correct answer be? Can you guys tell me what is the correct answer for this? Can you guys tell me what is the correct answer for this? Will it be more or will it be less? Will it be more or will it be less? Will it be more or will it be less? Come on, think about it. Think about it. I feel there is a problem in this. You know what is the problem? Just imagine. Actually, 4 amperes of current is flowing. 4 amperes of current is flowing. But not all of that 4 amperes goes here. Maybe 3.9 ampere goes here. Maybe a small current goes over here. Because of that, the resistance is actually small. The resistance will be different, The current is small. So if I measure the actual resistance, it will be voltage. Voltage is 20, but instead of current being 4, it will be 3.9, which means it will definitely be more than 5 ohms, because when you make the denominator smaller, the ratio increases. So it won't be 5. Instead of 4, if you make it 3.9, it will go more than 5. Hence the answer is option B. Option B, exactly. That's the answer. So when you perform Ohm's law experiment and you connect a voltmeter and ammeter and you measure the resistance that you get, let's say it comes out to be 70 ohms, the actual resistance will be slightly less than 70 ohms. Maybe 69.5 ohms, 69.8 ohms. That depends on how the current gets distributed. But it will definitely be less, because you cannot have an ideal voltmeter in real life. Moving on to the next question. There is a galvanometer, has a resistance of 10 ohms, sensitivity of so much, 100 divisions on the scale. Okay, I think this particular question has again come over here. I think this was the old galvanometer question. Guys, this has already been done. I'm just skipping this. Okay, this was done in galvanometer. Okay, I think it has just come over here by mistake. Okay, let's have a look at this. A galvanometer having coil resistance 100 ohm gives a full scale deflection when 1 milliampere of current is passed through it. What is the value of the resistance which can convert this galvanometer into a voltmeter? What is the value of the resistance which can convert this galvanometer into a voltmeter, giving full scale deflection for a potential of 10 volts? For a potential of 10 volts. See, very good. Priyanka, looks like you guys are attentive. So over here, I can see that the maximum voltage that I can measure is 10 volts. The maximum current that can be passed is 1 milliamperes. The resistance of the galvanometer is 100. I have been asked, how will you convert it into a voltmeter? That means I have been asked, what is the resistor that you will connect in series? Let me just think of the diagram first. So I have the galvanometer over here. This is your galvanometer of 100 ohms, and then you have your series resistance, that's it, and you can measure a maximum voltage of 10 volts, for a maximum current. How much is that current? It is given to be 1 milliamperes. Voltage is current into resistance. Voltage is current into basically resistance. The voltage is basically 10. Current is 1 milliampere. That means 1 into 10 to the power minus 3. Resistance is 100 plus Rs. That's the total resistance. So this will go over here. This will become 10,000. This will become 10,000 is equal to 100 plus R. So therefore, the resistance will be 10,000 minus 100, which will be 9,900 ohms. So basically it is 9.9 kilo ohms. So 9.9 kilo ohms is option B. Option B is the correct answer for this. Yep, perfecto, amazing. Kudos to all of you. Amazing, my dear students. So if you draw the diagram, it actually becomes a very simple problem. If you try to by heart the formula, it might look very scary. You should just understand, the range of the voltmeter is 10 volts, maximum current is 1 milliampere. So when maximum voltage is there, maximum current is there, and voltage is current into the total resistance, which is Ohm's law. So basically use Ohm's law and you get the answer. That's it. Nothing's great, nothing very revolutionary about it. Okay. So voltmeter done, galvanometer done. Let's go to ammeter now. Ammeter will measure, like I told you, current. And ammeter at the end of the day, I have told you, it is nothing but a galvanometer, but you modify it. Okay, so when you have a device, and you want to measure the voltage, you connect voltmeter parallel to it. But when you want to measure the current passing through the device, you always connect the ammeter in series. Ammeter is always connected in series with the device across which you actually want to measure the current. So if you want to measure the current through the device, you cut the wire at this point and this point, you insert that ammeter and let the current flow, and then see how much current is flowing through it. That's it. That's how you measure the current. So what exactly is there inside an ammeter? Let's understand. But before that, will ammeter have a very high resistance or very low resistance? Answer that in the chat box. Will it have very high resistance or very low resistance? Think about it. Because the ammeter is connected in series, imagine if it had very high resistance, then it will block the current. This device will not work only. When you insert this ammeter, it should not affect the current which was actually flowing before inserting it. Before inserting, whatever current was flowing, that same current should still flow, right? That means this should behave almost like a wire. And what resistance does a wire have? Very little, negligible. So ammeter has very low resistance. Keep this in mind. So ammeter has very low, exactly opposite of voltmeter, very low resistance. So can you think, how do I make a very low resistance? Well, simple. What you do is take a galvanometer, okay, and you connect basically a resistance in parallel. Basically it is called as a shunt resistance, a low shunt resistance. That's it. Together, this particular device, this apparatus, is your ammeter, is basically your ammeter. That's it. That's what an ammeter is. So now you will see that this device as a whole has very little resistance, because whenever you connect resistors in parallel, the net resistance becomes smaller than each of the resistance. Like when you have resistors in series, the total resistance is bigger than each of the resistance. You add all the resistances, that's how you get the total one. But in parallel, when they are in parallel, shunt basically, then the effective resistance reduces. So that's why you have made it very small resistance and then connected it, and now you see that it can not affect that device at all. Alright, so same current will flow. Exactly. Alright. Now, what exactly are the formulas, the working and other diagrams that you should know inside an ammeter? Let's go to that. So let's start by drawing the galvanometer first. So this is your galvanometer. This has some resistance Rg. Okay. We connect a shunt. Shunt means parallel. So I will just show this here. This is called as the shunt resistance. Together both of them is my ammeter. Now what happens is a huge current or a decent amount of current might enter inside. A good amount of current might enter inside, but if you let this current pass through the galvanometer, like I have told you before, galvanometer has a maximum deflection current. That current is usually very small, in picoamperes, microamperes, sometimes even in milliamperes. So if a decent current is passing and that same current goes through the galvanometer, that galvanometer will burn, that instrument will be damaged. So you want this traffic to bypass from here. So you want very little current to go here. You want the remaining current to go through this point or through the shunt resistance like this. And again it will collect back over here and you will get back the original current. So here the current is basically Ig. Here the current is basically Is. So to do that, the shunt resistance should be very small. That's why I also mentioned it over here, low shunt resistance. The moment the shunt resistance is low, most of the current will bypass through this and very little current will go, just enough to measure how much this actual current is. Just enough to measure how much this actual current is. Is that clear, my dear students? Everybody with me? Perfect? Awesome. Now we can see what all equations we can write by using Kirchhoff's current law. Can I say, by using Kirchhoff's current law, the current entering in this particular node is the current entering out. So it is IS plus IG. IS plus IG. This is one equation. If needed, you can use it. There is one more equation, equation 2, which you can use over here, and that is basically, remember, RS is parallel to RG. When such things happen, the voltage difference is basically same. Resistors in parallel, what is same? The voltage, the potential difference here is same. What is the voltage difference across this resistance? Across this resistance, current into that resistance. So can I say IS into RS will be equal to, what is the voltage difference across this resistance? This current into that resistance. So IG into basically RG. So this is another equation which you can use, and whatever is asked, whether IS is asked, IG is asked, RG is asked, or RS is asked, using these two equations you can find anything that you want. Using these equations you can find anything that you want. So this is one equation which is obviously important, and this is another equation which is again very important. So both these equations are good enough for telling you anything else. Most of the other data will be given to you. When we see the problems, you will understand. But at the end of the day, do you realize it is just parallel resistors theory and Kirchhoff's current law? That's all. Equivalent resistance, that's it. That's all that is actually technically there. Everyone with me? Cool? Awesome. Chalo, let's solve some questions which are coming up on your screen. Here is the first one. If there is an ammeter connected in parallel to the device instead of series. Interesting. Usually you connect ammeter in series, but now you have connected it in parallel. So then what do you think will happen? It will show voltage instead of current. It will not deflect only. It will show maximum deflection and the coil may burn. The functioning won't be affected and it will still show the same deflection as when connected in series. What do you think is the correct answer for this question? Come on, my dear students. Come on, think about it. Think about it. Thank you, Gopika, so much. Come on, everyone, let me know. If ammeter is connected in parallel to the device instead of series, then it will show voltage instead of current, it will not deflect, it will show maximum deflection, coil may burn, or do you think the functioning won't be affected? It's connected in parallel. The moment you basically connect the ammeter in parallel, what happens is that all that current will go through the ammeter. Very little current will go here. So large current will basically damage the device. It will exceed the full scale deflection. It will burn it. So hence the answer is C. Exactly. Option C. C for Captain Shreyas. Perfecto. That is the correct answer. Next question on your screen now. The net resistance of an ammeter should be small. So what do we ensure by that? It does not get heated. It does not draw excessive current. It does not change the current which we are trying to measure. It can measure large current. Imagine you are the doctor and you want to measure the amount of blood flowing through a blood vessel of an actual person, artery or something. If you place a device, that device should basically do what? Think of current like the blood flow. Think of the device trying to measure the blood flow as the ammeter, and think what should happen and what should not happen. Obviously, when you put the device, the blood flow should not be affected. Or you put the device, the blood flow only stop. And then you are like, sir, the reading is this much ml is flowing per minute. Arey, that person died. What are you doing? The blood flow should not be affected when you are doing that measurement. Yes or no? Same way over here, when you're trying to measure the current flowing through the device, you would want that the current actually does not change much. So that's why you keep it very low resistance. So the resistance does not change the current which you are trying to measure. Option C. No, it does not draw excessive current. No. That is not true. It is not true. That is true for voltmeter. That is true for voltmeter. Voltmeter has very high resistance so that it does not take in lot of current. It allows the current to still flow through the device. That's why voltmeter is in parallel. Option B will be correct if it was for a voltmeter, and that too it will be given the resistance of a voltmeter is very high because it should not draw too much of current. It should allow the current to still flow through the device. Is that right? Everyone with me? So be very careful. These kind of statement based questions do come. If you have analyzed the last few years paper, these kind of concept, these kind of tricky questions, these kind of theoretical questions do come in the NEET examination, right? Moving on to the next one on your screen. This is a numerical based question. Galvanometer's resistance is given. Full scale deflection current is given. Question is, how do you convert it into an ammeter of 1 ampere? Let's understand the diagram first. Imagine this is your galvanometer. It has a resistance of basically 20 ohms. Okay, it has a resistance of basically 20 ohms. You want to connect a shunt resistance. Obviously, it should be in parallel. So wherever you see series, eliminate those options. Series can't be the correct answer. It will be either this one, option B, or option D. It can't be series. You always connect it in parallel. So this is your shunt resistance. Now what happens is, basically it is clearly mentioned that you want to measure currents up to 1 ampere. That means if technically 1 ampere current comes over here, in spite of that, this resistance cannot handle, this galvanometer cannot handle more than 5 milliamperes. So where is the remaining current going? Obviously through this resistance. And that will be 1 ampere minus 5 milliamperes. How much will that be? 1 ampere is a large current, 5 milliamperes is a very small current. Large current minus small current will be that large current only, big large current. So it will still be approximately 1 ampere. Everybody agrees with this? I've indirectly used Kirchhoff's current law. This current got distributed into 2 branches. This is very large as compared to this, so ignore this. So this current is roughly equal to this current, approximately. That's why this symbol. Now we know that the voltages are same. The voltages are same across both of them. So voltage is same. So I can say basically IS into RS will be IG into RG. What is current through the shunt? It is 1 ampere. What is the resistance of the shunt? That's what we have to find. What is the current through the galvanometer? 5 milliampere. So 10 to the power minus 3. What is the resistance of the galvanometer? 20. Right? So this will become 5 into 20 is basically 100. 100 into, so this will be 100 into 10 to the power minus 3, which is basically 0.1. That is the shunt resistance. So 0.1 ohms, that's option D. Yes, there you go. That's the correct answer. Perfecto. Yep. Is there any chance to take only one subject, J English, paid batch? No ways, Rakesh. That's not possible only. And anyways, the fees are very less. So it's less than the tuition fees of a CBSE teacher. A CBSE teacher charges some 2,000-3,000 per month, at least tuition. You can inquire anywhere. So the fees of this batch is less than the tuition teacher of CBSE for one subject. Okay, for boards. And here we are teaching you for NEET with test series, with DPPs, with all the strategies and all the mentorship and doubt groups. That too for all the subjects, and that too at this price. I mean, you can't go lower than this, right? Moving on to the next concept, and that is potentiometer. So voltmeter done, ammeter done, galvanometer also done. After this lecture, 100% you will not face any difficulty with these instruments. After this lecture, 100% you will be confident to attempt these questions. After this lecture, you will get an head start and you will feel like doing more questions from this chapter, and if a question comes in NEET, 100% you will crack it. So please attempt and practice a lot of questions after this class. Don't stop the studies over here. Yep. All right. Great. Hello GLG Slavan. Yep. Now potentiometer. Potentiometer is a very interesting device. because it can be used in different ways to measure different things. So a potentiometer is more likely a bulky and costly instrument, and also the measurement is tedious. Measurement is a procedure. You have to do this, do that, do this. So measurement is basically, sometimes you can say, tedious as compared to a voltmeter or ammeter, where you just connect the voltmeter, you get the voltage. You don't have to use your brains over there. Just connect it. Connect the ammeter, you get the current. That's all, right? But this is not so easy. You have to do some things, then calculate, then you get the answer. All right. But this device is more accurate. This device is more accurate as it is based on a method called as null deflection method. Null deflection method. So the readings that you get are very, very accurate. So that's why we use this. If there are only disadvantages, obviously we would not be using or studying this procedure. So it's a very, very accurate device, and it uses null deflection method. A potentiometer has the following applications. So number one, it can be used as an voltmeter. It can be used as an voltmeter. It can also be used to compare EMFs. It can also be used to compare what? EMFs. It can also be used to measure internal resistance of a cell. To measure internal resistance of a cell. So these are the three major applications to compare EMF. Oh, this is 2 volts. How many volts is this? What is the internal resistance of a battery? All batteries have some internal resistance. And it can be also used to measure the potential difference between 2 points. So we'll see the diagrams for all the three of them. But let's understand what is the basic setup of a potentiometer first. Is this clear, everyone? Everybody clear with this? What are the applications and what is the advantage or disadvantage of a potentiometer over voltmeter and ammeters? Right. So essentially, a potentiometer device has a wire, highly resistive wire. This is a resistive wire, and it has some resistance. Maybe I call it RP. Okay. It will have some length also. This is the length of the wire. You can say this is the length of the wire, and this wire is basically connected to a battery, maybe with some internal resistance, maybe some external resistance might be there, and all of that. Totally, I will call that resistance as R. This is the total resistance, okay, of the circuit. This is some battery's EMF. This is called as the driving circuit. This is called as the driving circuit. Now the device across which you want to measure the voltage, or the battery whose internal resistance has to be measured, or the batteries whose EMFs have to be compared, all that comes over here. All that comes on the other side. Sometimes this is drawn like this and the instruments come on the other side. It's okay, one and the same thing. So this is basically your main primary circuit, which has the driving circuit with a wire and some resistance, and you will see the other things whose measurement has to be done comes on the other side. Is this much part clear? Is this much part very, very clear, my dear students? So I'll just write this resistive wire over here. This is your potentiometer wire of some resistance, right over here. Don't you see that there will be some current flowing in the circuit? Don't you see that there will be some current flowing in the circuit? Let's say I call it I. Can I find out this current? I think so. What is the voltage supply? It is just E upon the total resistance. This is R and this has resistance RP. So it is R plus RP. Everybody gets this point. Current is the total voltage by the total resistance. Simple. Okay. Now why did I find the current? Why did I find the current? Because I want to find the voltage across these 2 points. Like, why am I finding the voltage difference? Because I want to find a new quantity called as the potential gradient. What is this new quantity and why do I need this quantity? You will understand it in a bit, because that quantity itself gives me the calculations for comparing EMFs, for measuring the internal resistance, or even making it act like a voltmeter. So finding some quantity called as potential gradient is of priority. Before we go ahead, see the 3 applications. To find potential gradient, first thing we do is actually find the voltage between these 2 points. What is the total voltage across the potentiometer wire? That voltage across the potentiometer wire, won't it be the current into its resistance? That current is already known, so it is E into Rp divided by R plus R. That is the voltage of the potentiometer wire. Now, like I said, there is a new physical quantity called as potential gradient. Potential gradient of a potentiometer. This is how much is the voltage drop per unit length, delta V by delta X. Change in the voltage per unit length. If I move 1 meter, how much is the voltage change? So here you can see it is Vp divided by the length. So hence this whole thing, E into resistance of the potentiometer into R plus Rp, and this multiplied by the length. So that is your delta V by delta X. That is your potential gradient. Is that clear? Now, will you by heart this formula? I suggest not to do. It's okay even if you do not by heart. Main thing is you should know how to find the gradient. This procedure is important. First finding current, then using Ohm's law, and then saying that voltage gradient is voltage per unit length. So at the end of the day, this is nothing but your Ohm's law, nothing great. Even this is also Ohm's law only. Current is voltage by resistance, right? So if you know Ohm's law and basic knowledge of gradient is voltage per unit length, you will just divide the voltage with the length, you will get the answer. Is this much point clear? Is this much point clear? Okay, all right. Definitely, Gopika, maybe you can leave a comment or maybe you can message on Telegram or Instagram. I will definitely help you out. Don't worry about it. Where to start physics from, right? All right. So going ahead after this, once I talk about voltage gradient, why is it so important? I will tell you. See, if I tell you that there is a wire, potentiometer wire, and I tell you that the voltage gradient is, example, 2 volts per centimeter, example. All right. Now I take some 2 random points, one here and one here, and let's say they are separated by maybe 10 centimeters. Will these 2 points have some voltage difference? Yes, because this wire has a gradient. That means every centimeter I go, there is a voltage drop of how much? 2 volts. So if I move 10 centimeters, how much will be the drop? So it is nothing but your potential gradient, and let's say this length is X into basically X. So that is 2 volts per centimeter into 10 centimeters. So that is basically 20 volts. 20 volts is the voltage difference. So by the gradient, I can find the voltage difference between any 2 points on the potentiometer wire. Is that particular point very clear? So using this formula, which is that formula? This one. The voltage is potential gradient into X, the length between or the distance between those 2 points. I can easily basically figure out the voltage between these 2 points using this formula. Perfect. So keep this in mind. Now we'll see the applications in a bit, but before that, let's solve some basic questions. Forget these other things. Just concentrate on the potentiometer wire. In the following figure, the resistance of wire AB. So your potentiometer wire is this one. This is your potentiometer wire. This is your driving circuit. Forget this. This is some external circuit which is connected. Ignore that for now. Just look at this circuit. The resistance of the wire is 10 ohms. Length is 1 meter. The potentiometer gradient is how much? We all know that because of this battery, there will be some current flowing in it. that current is shown right over here. Can you guess the value of the current? That value of the current will be the EMF, which is 2 volts, divided by the total resistance of this 15 is there, plus the wire's resistance is basically 10. So 2 by 25 amperes. 2 by 25 amperes. Yep. The NEET Avenger batch is closed, bacha. The last entry point was yesterday. It's closed. The admissions have stopped. Yep. That's why we made a video also. There were adequate community posts, telegram posts also telling that the Avenger batch entry is going to be closed. So we are not taking any more admissions. Okay. Now going ahead, the potential gradient is asked. So for that I need the voltage between those 2 points A and B. What is the voltage between the points A and B? It is the current into the resistance of that wire, resistance of that particular wire from A to B. It is 2 by 25 into resistance. What is the resistance? It is clearly mentioned as 10. So 10 goes with 5 2 times, 5 goes with 25 5 times. So it will be 4 by 5 volts. But the question is potential gradient. So delta V by delta X will be the voltage across this wire upon length of that wire, that is 4 by 5 divided by the length of the wire is 1. So it is still 4 by 5 volts per meter, which is 0.8 volts per meter. So 0.8 volts per meter is option A, of course. That is the answer. That is the answer. Exactly. Awesome. GLG, if you start a new batch or something, we'll let you know. But as of now, alright, the entry is closed. If something comes up, we'll definitely let you know. Alright. So moving on to the next question coming up on your screen. The current in the primary circuit of the wire is this much amperes. Specific resistance is this much. And the area of cross section of the wire is this much. Then the potential gradient in the wire will be how much? Interesting question. Current is this much. The resistivity is given because specific resistance means resistivity. Area is given, gradient is asked. Let's understand what this question actually means. So this is my potentiometer wire. It has some resistance. There will be some current flowing in it. There will be some current. Obviously, it has some area of cross section. It has some area of cross section. It also has some resistivity. So in order to find the potential gradient delta V by delta X, it is the voltage divided by the length of the wire. Now voltage across these 2 points, the voltage across these 2 points is the current into the resistance. Current into the resistance by Ohm's law. Correct? So this is just using Ohm's law. Now what is the value of resistance? We know it is resistivity into length divided by area. Rho L by A, everyone with me? Rho L by A, perfect. Now do you see that this L and this L gets cancelled? So what am I left with? It is basically I rho divided by area. I rho divided by area. Is that clear? Everyone with me on this? Perfect. Now do I know current? Yes. Resistivity? Yes. Area? Yes. So I think I have got the answer. So delta V by delta X will be current, which is 0.5, resistivity, which is 4 into 10 to the power minus 7, whole thing divided by area, which is 8 into 10 to the power minus 6. 0.5 into 4 is 2. So 2 divided by 8, 10 to the power minus 7, 10 to the power minus 6. These will cancel. It will become minus 1 basically. So this will be 1/4. 1/4 is 0.25 into 10 to the power minus 1. So it is basically, I think it is in millivolts or volts maybe. So I can say it is 250 into 10 to the power minus 3 volts per meter, or I can say it is 250 millivolts per meter. So 250, sorry, my bad. 25, not 250. I think I by mistakenly wrote 250. Yeah, 25 into basically 10 to the power minus 3 volts per meter. So that is 25 millivolts per meter. I think that should be the answer. Yes, option B, of course. Is that clear? Everyone with me on this? Awesome, awesome. Let's go to the next question, but before that, before going to this particular question, we need to study the applications now. Now we'll see the applications of the potentiometer, all the 3 applications, and then we'll go to the remaining problems. The first application of a potentiometer is as a voltmeter to measure the voltage. So what you do is you have the potentiometer wire, all right? You have the potentiometer wire. It is connected to your primary circuit like this. This has certain length, let's say L. It has certain resistance Rp. It also has some voltage gradient delta V by delta X. It's already known how to calculate that. I know this much length, this much voltage, this much length, that much voltage. If you have the device across which you want to measure the voltage, this is your device across which you want to measure the voltage. Maybe it's a part of a big circuit. So what you do is you take one wire from here. You take one wire from here, this point, and connect it at this point. So across one side, you connect this end of the wire. Don't connect this end at this end. No, not to do that. Take this point, take a galvanometer, and touch it maybe over here. Touch it on this resistance wire over here. See if it deflects. If it deflects, start sliding and see if the deflection increases or decreases. If the deflection decreases, continue moving it till it becomes 0. If the deflection is increasing, move it on the other side so that the deflection decreases. Basically, try to touch it at different points and see what is the deflection, and you will find one particular point, let's say J, where there is null deflection. J is the point of null deflection. Null deflection. Null deflection means the current through the galvanometer is basically 0. When such a thing happens, when the current flowing through the galvanometer is 0, means that whatever voltage is there between these 2 points is also the voltage between these 2 points. That's why current did not flow. Current did not flow. When does current flow? Current flows when there is voltage difference. But actually, this point and this point have the same voltage. Anyways, these 2 points were connected with a wire, so they have the same voltage. So if there is no current flowing, that means there is no voltage difference here. There is no voltage difference here. So whatever difference is there here is the same difference here. Is that logic clear? Let me know. Let me know. Physics is easy. This is already the least fees, bacha. I don't know. You can take a loan or something, or maybe pay through EMI if possible, or maybe just wait for the fees to reduce maybe sometime later in the crash course or something, right? All right. So, or else you have the NEET Conquer batch right over here on YouTube. So continue your studies over here meanwhile, okay? So don't stop your studies. Yes, Praveen S. Awesome. Praveen S. Perfect. Now I can say that the potential difference across the device is exactly equal to, if I call this particular point A, this particular point B, is nothing but the voltage across the points AJ, and the voltage between any 2 points. I just gave you the formula. If this distance is basically X and I know the voltage gradient, it is nothing but the voltage gradient delta V by delta X into that length X. That's it. That will give me the voltage across the device. As simple as that. These many volts per this centimeter or meter into that many meters or centimeters will give me the voltage across those 2 points. And these 2 points voltage is these 2 points voltage. That's all. So usually this X is called as the balancing length, or sometimes even called the length for which null deflection is obtained, whatever you want to call it. Okay, it will be very obvious in the question's language. So this is the formula to measure the voltage across any device. Alright, so that's why finding delta V by delta X is very important. Keep this in mind. Now the second application is basically to compare EMF. To basically compare EMF. So in that setup, what you do is basically This is your potentiometer wire. This is your primary circuit, some resistance. First of all, you take a battery. Maybe it has some internal resistance, that's okay. Take one terminal, connect it over here. Take the other terminal via a galvanometer. See where you get null deflection. So let's say this length is, let's say, L1. You get null deflection L1 for EMF 1. For cell E1, the null deflection is obtained at L1, at a distance of L1. Now using the previous formula only, the voltage across the device is this into X, potential gradient into X. So voltage across this battery, the voltage across this cell will be the potential gradient delta V by delta X into this distance, which is basically L1. Voltage of the cell, because actually no current will flow, the terminal voltage will be the EMF. The voltage across the cell will be E. There will be no IR because I itself is 0. Agree or disagree? Agree or disagree? There is no current. Remember, current is 0. So terminal voltage is the EMF across the battery. So it will be delta V by delta X into basically L1. Everyone? Now you take any other battery. Let's say this is E2. Connect the same terminal here, this positive. Maybe it has some internal resistance. Again via galvanometer. See where does it balance again. Maybe this is the new balancing length. Again, similarly, you can say E2 is delta V by delta X, the whole thing into L2. What do you see now? What can we do now? You can divide both of them. So basically divide both of them. What will you get? E1 by E2 is L1 by L2. This is again a very important formula, because using this formula, if I know the lengths, I can compare the EMF. What is the ratio? Or if I know this is 7 volts, 2 volts, 3 volts, I can find the other voltage of the other battery. So that's how you compare EMF using a potentiometer. We have used this logic only of measuring the voltage between any 2 points. So this is also a very important formula, you can say, voltage across any device. Perfect. Keep this in mind. Cool. So 2 applications done. Ready for the last application, the third application, my dear students? Ready for the third application, the last application? Yep. Definitely. I'll put up the community post. There will be videos also. Don't worry. The last application, where you have the potentiometer wire, you have the primary circuit. Okay. You take a battery whose internal resistance has to be measured. This is R, this is E. Connect it over here, and again via a galvanometer find out the null deflection point. You try to connect it at different points and see, maybe there is one point where you get basically null deflection. I will call that length as L1. Okay, I will call that length as L1. So basically this is the third application. This is the third application to measure internal resistance. To measure internal resistance. That is the third application. So the first balancing length L1 is with the cell alone. That's it. Nothing else is connected. With that battery, you measure what is the balancing length. Now what you do is you connect in parallel another battery. Connect in parallel another resistor of some resistance R, and then let the current flow through the same galvanometer. You will get some new balancing length. Connect R in parallel. So L2 is when the cell in parallel with that other resistance R. You will get a new balancing length. Then the value of this internal resistance, all right, is nothing but R into L1 by L2 minus 1. That's the formula. Straightforward, you will get the answer. You don't have to know the EMF, you don't have to know the other things, okay, in the circuit. Just using this formula you get the answer. The other resistance into old length by new length minus 1. That's it, as simple as that. Yep. Is that clear? Everyone with me on this? Beautiful formula, beautiful method. It's not very lengthy, but yes, it is quite a procedure, because you have to first connect the galvanometer, touch it at different points, measure that length, connect that resistor in parallel, then again see what is the new length, then divide the length, subtract 1, then multiply by R. You will get the internal resistance, but whatever values you get, whether here or even here, they are very, very accurate. That's why we use the potentiometer. That is complete potentiometer for you, my dear students. After this, you can solve any question with regards to potentiometer. Let's have a look at this. In an experiment, the length is 240 centimeters with a cell. On shunting it, shunting means parallel, right? With a resistance of 2 ohms, the balancing length becomes 120. What is the internal resistance of the cell? Basically, it is the third application, if you notice. This is the third application to measure the internal resistance. Shunting means basically parallel. If you notice, the length 1 over here is 240 centimeters with the cell. That's it. Only with the cell. Then it is L1. What is L2? When it is in parallel, parallel means shunting. So then L2 is basically 120 centimeters. How much resistance? Capital R is basically 2 ohms. Small r is basically asked. That's all, my dear warriors. Use the formula. R is basically capital R, L1 by L2 minus 1. Capital R is 2. L1 by L2 means 240 by 120 minus 1. 240 by 120 is 2. So 2 minus 1 is basically 1. So it is basically 2 ohms again. Okay, so it just comes out to be 2 ohms, the same thing, right? That's the answer. Perfect. C for Captain Shreyas. Very good. Priyanka, Vedanjani, Karthik, Pravina, Kirtana, Alekhya. Option C is the correct answer. Perfecto, perfecto. Moving on to the next one coming up on your screen. Here it is. There is a potentiometer wire 100 centimeters long. Constant voltage is maintained across it. Two cells are connected in series, first to support and then in opposite direction. The balancing points are 50 and 10. What is the ratio of the EMF? I think this is the second application. If you notice, first they are in supporting each other and later on they are opposite to each other. When they are supporting, the total EMF will be E1 plus E2. When they are opposing each other, it will be E1 minus E2. And we know the EMF connected in that potentiometer is directly proportional to the length. I just gave you that formula right over here. Correct? The EMF is directly proportional to the length, right? But here, both these batteries are in series, supporting, then opposite to each other. So that's why E1 plus E2 and E1 minus E2. So if I take this ratio, it will be L1 by L2, right? So basically E1 plus E2 by E1 minus E2 will be L1, which is 50 and 10. So 50 by 10, 0, 0 cancels. Now you can basically cross multiply. So E1 plus E2 will be 5 E1 minus 5 E2. Bring E2 on this side, bring E1 on the other side. So it will become 6 E2 is equal to 4 E1. So E1 by E2 will be, E1 by E2 will be nothing but 6 by 4, which is 3 by 2. Yep, 3 by 2 is option D. Yes, that's the correct answer. D for doctor. No, it is not A. Be careful. Thank you, Sangeeta, so much. Right? Yes, and I hope you guys are smashing the like button as you are watching this class. Don't just watch the lecture for the sake of it. You have to smash the like button. Very, very important. Okay. So these are how the potentiometer problems are. So I've kept one homework question also for you. Make sure you solve this question and post the answers in the comment section. I'll be waiting eagerly to see all your answers. As soon as the session ends, I want you to answer this particular question, right? So that's it from today's session, my dear warriors. I hope you enjoyed a lot. I hope you learned a lot. This current electricity chapter mainly is done. Obviously, there will be more problem solving sessions later on. But for now, this chapter is over. We'll be starting off with magnetism next. and after that we'll be continuing with circular motion, work power, energy, all those things as well. Don't worry. Okay, so that's it for today's class. Bye bye, have a great time. Hasta la vista. God bless you all. Take care.